All right. So we've actually already kind of taken a little bit of a peek at a quadratic. We've been working a lot with the function y equals x squared. That's a quadratic. So with lines, we said you can look at the highest power of x and see that it's 1, and that tells you the function's linear, right? With quadratics, you look at the highest power of x in the equation, and if it's a 2, we know it's a quadratic. So on that graphs, you should know, we saw just the most basic kind of simple quadratic that we have, and that's y equals x squared. So if you look at, right, the graph of y equals x squared, right, it looks like this. It goes through the origin, and it's the graph, it's always going to look like a parabola. So then, what we're going to see, we can make some adjustments. We can shift and move and flip this guy upside down and shift it around. It's still going to have the form of a parabola, and that parabola will either open up or it will open down. So when we're looking at quadratics, the kind of most complex form you can see is going to be the following. So there's sort of two common forms for quadratics, right? We can see it written as ax squared plus bx plus c. So this is what a lot of you guys saw in high school. So this would be expressed as a polynomial, right? Where a, b, and c represent real numbers. They're just, those are going to be the coefficients of those three terms. Or by rearranging this guy, we can use another form of the polynomial. Well, it's not a polynomial, excuse me, another form of the quadratic. And this doesn't really have like a formal name, but I kind of, and I've seen it called in books like vertex form. So we could actually rearrange the equation on top and turn it into the form on bottom. And so just like we had with like circles, where when you put a circle in standard form, you could pull the center out. When you put a parabola in this form, you can pull the vertex directly out. So the vertex of this parabola, right, is going to be h comma k. And there's two ways we can go from the first form to the second form. So before we get into the algebra and kind of get into the weeds of doing that, let's just talk about like some common attributes of quadratics so we kind of all know we're on the same page. So first and foremost, right, when we say it's opening up, right, I'm saying it opens up like a cup, right, and if we flipped it upside down, right, we call it opening down, right? The vertex is always going to represent the turning point of the graph, right? And so the vertex will always be a minimum, right, if you're at the bottom, or if we flip it upside down, the vertex would represent a maximum. So this guy right here is technically in ABC form, right? It's in this where A is 1, right, B is 0, and C is 0, right? But if I wanted to write this in vertex form, right, well, it would simplify, right back to x squared. But if I wrote this in vertex form, you can see the h value of the vertex is 0 and the k value of the vertex is 0. So this one's kind of silly because it's just too basic, but we're going to move it around in a minute and let you see what's going on. All right, the other thing you want to pay attention to on this graph is the leading coefficient. So the leading coefficient of the squared term, or the a value, is positive 1, okay? So it is not the value of a that determines whether a parabola opens up or down. It is the sign of a that determines if it opens up or down. So here, right, a is positive 1. So what we say is if a is a positive value, right, the parabola opens up. So when the parabola opens up, right, the vertex is the minimum, and more specifically, it represents an absolute minimum on the graph. The graph will never go lower than the y value on that point. So this is an example of a function that we might ask for you to give the domain and range of off the equation, right? So for domain, we actually have those algebra rules we can look at, right? We can look for radicals, we can look for denominators, we can look for logs and kick values out. Well, since a quadratic's just a polynomial, right, none of those things come into play, so the domain of a quadratic is going to be all reals, just like the domain of a line is all reals. But a lot of times we'll ask you for the range. And so there is no kind of algebra trick right now to figuring out the range. But if you know that what the equation you're looking at is a parabola, and you know whether that parabola opens up or opens down, the range should be a snap. So if the parabola opens up, well then the vertex is the minimum of the graph. So in this sense, the range will be from whatever value k is, because the range gives the y values, up to positive infinity. So you can see this right here. This graph goes from this y value, which happens to be 0 in this case, and the graph will continue on to positive infinity. If a is negative, so if a is a negative value, then what we've done is we've multiplied the function by -1, right? And when you multiply a function by -1, you flip it over the x-axis, so that would make sense that it would make the parabola open down. We've reflected it over the x-axis. So when a is less than 0, the parabola opens down. So now the vertex is the absolute maximum on the graph. There will be no point higher than that. So the domain is still going to be all reals, but the range will go from -infinity up to and including the value k. And so you always have to make sure you're using square brackets around whatever k is, because it is included on the graph. It is the maximum that's there. So when we tell you that we ask for range of some of these things, the equations are structured in such a way that you should be able to kind of visualize the graph in your head. And you're kind of mentally reading the range off the graph, or you should be able to just sketch it really quickly and read the range. So parabolas will either open up or open down, and the vertex will either be a maximum or a minimum. And that's what you'll use. So when we ask you to find the range, that's another clever way of asking you to find the vertex, because you need the vertex to give the range back. Does that make sense? All right. So similarly, later when we get into word problems, we're going to talk about finding the maximum and minimum value of functions. And if you do some algebra and work with the function you were given, sometimes it doesn't look like a quadratic, but if you distribute something or rewrite it and you see, oh, this is a quadratic function, well then the first thing you want to check on that quadratic is if they ask you to maximize, well then that better be a quadratic that the parabola opens down, because if it opens up, the maximum value is positive infinity and you can't maximize that, right? So if they ask you to minimize, right, you want to make sure that that parabola opens up, and that's another way of saying, when they say find the max or find the min, that's another way of saying find me the vertex, because that's where the graph tops out or bottoms out. All right, so let's look at how we kind of can convert between the two forms. So there's nothing wrong with the ABC form. That's the form a lot of us worked with in high school. There's a lot of stuff we can do with that form. However, when it comes to graphing or maximizing, vertex form is much more useful because we know the location that it tops out, or we know the location that it bottoms out. So there's a couple of techniques you can do to convert a quadratic from one of these forms to the other. So let's look at an example. Oops. Okay, let's say we have this guy. And I want to find the vertex of this parabola. So I can put it in vertex form, and there's two methods you can use. One is definitely easier than the other, right? So the first method we can use is we can complete the square. So completing the square is a little bit different when you're doing it with a quadratic than when we did it with circles. So conceptually, we're still going to be looking for the same term, but in a circle, you had two sides to the equation. So remember, whatever you added to one side, we had to also add to the other side of the equation. This, however, you don't really have the other side of the equation. So when you complete the square and you don't have an equal sign to add to both sides, you have to do it a little bit differently. So just like we did with circles, right, the goal was to factor this into x minus h squared. Well, if we look at our vertex form right here, that's what we want to happen here too. We want to get an x minus h squared. So that's why we want to complete the square here. So the first thing that I want to do is I want to group everything with an x together. And I'm going to shift the constant to the other side. So on a circle, we moved it to the other side of the equal sign, right? Here, we just put it outside of these parentheses. We're just going to kind of punt it for now, all right? And just like we did with circles, I know that I need this to factor into h, right, minus something squared. So I can do this in kind of two lines. So when we did this for circles, right, we said, well, divide the middle term by 2, right? It was negative b over 2a. So if I divide the middle term by 2, I'm going to get negative 3. So that means I'm going to have a minus 3 down here, right? But we're completing the square, so remember we had to add this number squared to both sides. So here's where things get different. On the inside, you're still adding plus 9, just like we did with the circles. But because there's no equal sign over here to add 9 to the other side, I have to subtract 9. So what I've done here in this top line is I've added 9 and subtracted 9. So that's the same thing as saying I'm just adding 0. And if you add 0 to something, you don't change its value. Question?
Why is it not x plus 3 if it's like minus negative 3?
So it's going to be minus because this is a minus sign, right? So if you look here, what the value of h is negative b over 2a, which is positive 3. But the structure of this equation, when I pull h out, it does come out as a positive 3. But algebraically, the sign here will match the sign here. Yep. So you have to add and subtract on the same, because you're on the same side of the equation. So you're adding 0. If you had an equal sign, well, then you can just add to both sides. And that's the same thing. If I added to both sides, well, then technically I'm allowed to grab that 9 from the other side and pull it over and subtract. So this is a little bit more complicated for people than working with circles. So then over here, if we simplify our constants, well, 8 minus 9 is negative 1. So that means this is actually going to end up being a minus 1. So now I'm in vertex form, where the vertex of this parabola is 3, negative 1. Notice that the sign of h appears to change when you pull it out because it's inside of a function. And the negative 1, the k, just comes down directly. So it's just negative 1. So the sign of h will flip, but the sign of k will stay the same. If you graph this in a graphing calculator and you graph this, you'll get the exact same picture. They are completely equivalent. So if we were to FOIL this out and then simplify, it would turn right back into that. Right? So this is vertex form. So I don't necessarily recommend doing this way, but if you look in a textbook, if you look on Alex, sometimes this is how they teach you to do it by completing the square. All right, so there's another much easier way, which is the following. The value of h, right, when you start out in ABC form, is negative b over 2a. So for this particular parabola, right, if we look at it, well, negative 6 gives you positive 6. And then a was 1, so we're going to divide by 2, so h is 3. If you want to find k, well, since k is the y value that comes out when you use this point, right, k is just f of h. So you plug 3 into the original equation. So you'll get 3 squared, right, minus 18 plus 8, and this does in fact work out to be -1. And that's what the vertex is. You plug in that x value into the equation, that y value comes out. So then if you know the standard form, kind of like with what we did with circles, right? If you knew the standard form of a circle and I gave you the center and the radius, you just had to pop them into the equation, right? So then the question comes, well, what about A? We didn't solve for A. Well, the A value in this form and the A value in this form are the same A. So you don't actually have to solve for it all the time if you've actually got the original ABC. So since A was 1 here, A is going to be 1 here. So A, right, is going to be 1. So now I just plug in the values that I have. So A was 1, H was 3, and K was -1. And I get right back to the same vertex form without having to complete the square. All right, so where does this come from and why does this work? Okay, so if we wanted to solve so let's talk about solutions. To quadratic functions, right? So when we were all in high school, myself included, right, and we first saw quadratics, we would see it typically in ax squared plus bx plus c, right? And whenever they talk about the solutions to a quadratic function, or they ask you to solve an equation, and just in general when you're given a function and they say find the solutions of, they're asking for the x-intercepts, right? You just set it equal to 0 and you solve. So the solutions, right, is the same thing as asking you to find the zeros of a function. That's another way we could ask you to find it. That's the same thing as asking you to find the x-intercepts. All three things, right, is telling you to find the locations of the points x comma 0. So it's telling you set y equal to 0 and solve for x. So there's multiple ways we can ask you to do this in an equation. So the way we did this, if you have an equation ax squared, right, plus bx plus c equals 0, you have two options. The first is try to factor. If it factors, factor it and look at the result of each factor, right? All right, so let's look at something like this. So x squared minus x minus 6 equals 0. So this actually will factor, and you can check very quickly if something will factor by looking at the last number in the term. You can look at c. And so you just ask yourself, well, what combinations of numbers give me 6, right? So 1 times 5 or 2 times 3. Those are the only two that you can break it down into. Or sorry, 1 times 6 or 2 times 3. So then what you can do is, let's talk about 1 and 6. So with 1 and 6, you're either going to add or subtract those two numbers when you FOIL out what you factored. So 1 and 6 will add to give you 7, or they will subtract to give you 5, right? Plus or minus 5. So the middle term is not 7 and is not 5, so we throw those out. We don't even have to look at those, right? 2 and 3, right, will either add together, the biggest they'll be is 5, or the smallest they can ever be is 1 if you subtract them. Since the middle term is 1, well then let's try to factor with 2 and 3. So you can actually toss numbers out very quickly by adding and subtracting them. And it doesn't matter plus or minus up front because we can deal with the signs when we actually go to factor. So if we look at this, right, 2 and 3 are the only logical choice. So x is only going to break down into x and x, right? And the only way you're going to get a -6 is if you multiply a positive number times a negative number, right? If they're both positive, they multiply out positive. If they're both negative, they multiply out positive. So if the sign of C is negative, well then you know the signs here, right, have to be opposite. So then the question is, well, where do you put the 2 and where do you put the 3? Well, since I want them to add to -1, then I need the larger number to be negative, so they add up to a negative number. So I'm going to put 3 here, right, and 2 here. If that had been a +1 for the middle term, then I would have made 3 positive and 2 negative. So they would have added up to +1, right? So then the next step is, well, then you just set each piece, right, equal to 0, and we would see the solutions here are -2 and 3. So it's really, really easy if you can see how to factor it to solve the problem. That's always sort of the optimal way you want to do it first. All right? But what if we have something that doesn't factor, right? So the second option you have is to use the quadratic formula. All right, so let's say we want to solve this. So this isn't going to factor because all I have for C is a 1. 1 only splits into 1 and 1, and 1 and 1 will either add to 2 or subtract to 0. So since the middle term is not 0 or 2, I'm stuck. This doesn't factor at all, okay? So then what you can do is we can say, well, the solution can be used by the quadratic formula. And so the quadratic formula says, well, the solution, right, will be -b plus or minus the square root of b squared minus 4ac all over 2a.
Wait, how do you determine that you can't factor that one out?
So 1 only split into 1 and 1, and it either adds to 2 or subtracts to 0. So if the middle term wasn't 0 or 2, it's not going to factor.
And when you say like the x's or like solutions, you're just talking about the y-intercept, x-intercept?
Yeah, so that's what that means. So they'll just sometimes say in a question, find the solutions to this function. It is implied you're setting the function equal to 0.
Okay.
If they say find the zeros of the function, that doesn't mean plug in 0, it means when's the function equal 0. And that's another way of saying x-intercepts. So those are all equivalent statements. So there's lots and lots of ways we can say set this thing equal to 0. And so that's one of the things that really trips students up on exams is they may know exactly mechanically how to do the math, they just don't really recognize like what they're reading, the instructions are being asked to do. And so that's why when you're studying, you don't just want to look at doing the computations, you want to look at the questions and sort of make notes on how are all the different ways they ask me to do the exact same thing. Right? And you want to kind of make sure you got the vocabulary down. Just like with lines, right? A linear relationship means a line between the two variables. Find me a linear model means find me a line. Find the equation of the line clearly means find me a line. So there are lots of different ways we can ask you to find me the equation of a line using different words. Okay, so if we try to solve this using this formula, right? Clearly A is 1, B is 1, and C is 1, right? So x, right, is going to be -1 plus or minus the square root of 1 minus 4 times 1, right, times 1, all over 2 times 1. So if I take this out one more line, well, under the radical here, I get 1 minus 4, which is -3 over 2. Well, since you can't have a negative under a radical, there are no real roots to this equation. So another way is there's no solution. So there are no values of x you can plug into this equation that will ever come out 0. So this thing's never going to touch the x-axis. Now you can look at the parabola and that kind of makes sense. It's a parabola that opens up, so the vertex is the bottom, and that last value you see, it's definitely shifted up in some way, right, from the original function. So what this is telling you is the vertex is above the x-axis and then it opens up from there. And so that makes sense. It's never going to cross the x-axis. You're just not going to find any solutions. Yeah?
So if that was a positive 3, how would you continue with the problem?
If that were a positive 3, right, so all I would have to do is, let's say, maybe change the middle term to negative x, right? Then you would get a positive 3 under the radical. And then your final answer would be 1 plus the square root of 3 all over 2, comma, 1 minus the square root of 3 all over 2. So that's how you read the plus and minus. It just means they're both happening, so you write it one with just the plus sign, you would write it one with just the minus sign, right? So let's talk about, right, now that we've seen the quadratic formula, let's actually talk about like what's going on here and why this thing, it gives you the vertex. How do we get the vertex out of this crazy thing right here, right? So in the quadratic formula, switch colors here. All right, so in the quadratic formula, this piece of the formula is called the discriminant. Okay, and so all that is the stuff under the radical. And it's the most useful part of the formula because the stuff under the radical, right, there's a restriction on it, right? That stuff has to be positive or 0 or you can't continue with the problem. So you can kind of think of the word discriminant as meaning it literally discriminates whether you're going to get solutions or not solutions out of the problem. It is the deciding factor in this of whether you get answers or no answers. So if, right, b squared minus 4ac comes out to be a positive value, right, then you get 2 solutions because you're going to have the plus case and the minus case. So you're definitely going to get 2 answers. And visually, right, this could look like one of 2 things. You could have a parabola that opens up where the vertex is below the x-axis, right? So there's it crossing the x-axis twice. Or we could have a parabola that opens down. And so if it opens down, the vertex needs to be above the x-axis, and that guarantees you're getting 2 solutions. So one of the things you want to make sure that you can do here is algebraically be able to identify whether you're going to get more than one answer, and then visually, if you're looking at a graph, understand why you're getting more than one answer. Okay? So these would be the locations of your 2 solutions. These would be the locations of your 2 solutions in this case. Right? So if b squared minus 4ac equals 0, then you get exactly 1 solution. So why would that be? Well, if we write this guy out, and we say everything under the radical, right, is 0, well, that means the square root of 0 is 0, right? So then if you simplify this, all you're going to get left is negative b over 2a. So if all the stuff under this guy is 0, the radical just disappears out of the equation, and you're only going to get 1 answer. The only way you can get 2 answers is you got to have the plus and minus and get stuff out of the radical. So visually, what this looks like, right? A quadratic by its nature, right, should have 2 solutions. So when this happens, we have what we like to call repeated roots. So what that means when you get a repeated root is graphically the turning point itself is on the axis. So basically the 2 intersections that you would normally see are right on top of each other. So that's when the turning point lies. So graphically it's going to look something like this. Right? You could have a parabola that opens up whose vertex is located right, on the x-axis. So that would be your one unique solution x, right? Or we could have a parabola that's opening down, right, but the vertex is still lying on the x-axis. So that's why you're only going to see one intersection. If we, right, if we say, well, if, right, b squared minus 4ac is negative, right, we get no real solutions. A little scary. We were supposed to have a tornado drill today, and we got the email yesterday. They were canceling it was like fire drill or tornado drill. I think it was a tornado drill because it was going to rain. So they canceled the weather drill because of bad weather. I was like,
They rescheduled it to Friday.
yeah, they rescheduled it, but it just like made me laugh. I was like, yeah, the weather's going to be too bad to pretend that the weather's bad, so we're going to move that to another day. All right, so in this case, right, if we have no real solutions, that means the parabola isn't touching the x-axis at all. So we could have a situation where the parabola opens up, but the vertex is above the x-axis, so it's never going to touch, or the parabola is opening down and the vertex is below the x-axis. So we should be able to see in both ways whether we're getting solutions or not. So the punchline to this is when we, right, when we complete the square, right, or right, use h equals negative b over 2a, right, we are finding the one unique solution to the expression, right? And that's why it's giving us out the vertex. So when we're completing the square, we're technically not setting the quadratic formula equal to 0. In a way, it's a weird way we're not. We're finding the one unique h that gives you that corresponding k value at the vertex, right? When you just use the quadratic formula in general, you're finding the solutions of where it crosses the x-axis. So we only want to have one result come out, right? And if you notice, when this one result comes out, that is in fact where we're placing the vertex at a specific location. So that's why if you just look at that one isolated piece of the equation, it will in fact give you the vertex, or the location of the vertex of where it makes that turning point on the graph. And then, right, by plugging h into the expression, right, it will give you the corresponding k value. So that's what the vertex is. At that value, h, k is the y value that comes out. So if we use this for something that looked like this, right, h would be whatever the x value was, where it's located, and the k value that would come out of the function would be 0 in this case, because those points lie on the axis, right? But we can pick it up and slide it anywhere we want. All right. Oh, yeah. And back up here, I remembered one more way of asking this, right? Roots is another way. We can say, find the roots. That's another way you'll see that worded. All right, so let's call it for today.